Okay, so good morning, class. So maybe we just try to start on time. So before we start, so do you have any questions so far? So for today's lecture, so we're going to quickly talk about some size distribution of aerosol, because most of the time we are talking about not a single aerosol, right? So we talk about the so-called polydispersed aerosol. So that means that you can see, so you have aerosol with different size, and the different size means so you have different number concentration. And also to present this kind of aerosols, say size or surface or mass distribution, right? So we're going to spend some time to talk about like Gaussian distribution, okay? And then, so we'll talk about some of, say, when we have this kind of different process. For example, we're going to talk about the condensations or evaporation, right? So how you will affect like the aerosol size distribution, okay? And also we're going to talk about the coagulation, okay? So when you have two particles, so let's say they hit each other, right? So they will stick together. So this will, of course, affect the size distribution of your aerosols, but also that will affect your aerosol number concentration. So we're going to talk about this. Okay. So, but before we continue or we start, so do you have any questions so far? Okay. And then one last point I want to mention is, I think in the next section, so we're always going to give you some idea and also remind you to prepare your term report and also a presentation. And also for the PG, so remember, you also need to do your literature review. So we're going to talk about this in today's lecture. But let's spend some time very quickly to go through like the aerosol size distribution. So we're going to talk about this from an aerosol science perspective, okay? So if you remember, right? So last time, so we talked about the aerosol distributions. So we always use the log scale, right? If the x-axis, okay. But most of the time when you collect your data, so they are in your raw data, they are not in the log scale, right? So they give you a size bin and a different size bin, then you have a certain number, right? So somehow, so eventually you need to do some data manipulations when you present your data, right? So therefore, we stopped last time. So I think we stopped last time. So the idea is, so in case you have your aerosols same number distribution, right? So then you try to plot in the linear scale, you just have the same plot in the particle size, right? So this is your function, okay, for your number distribution. But if you want to convert these, right, to be some natural log, so this is just a log scale, right? So you know, x-axis, this is log BP, right? So this is a kind of the conversion, right? Say from this is just your BP, you convert to the log BP, right? So you have a kind of this conversion here. And here also give you another example, right? So in case you want the log scale, right? In the log scale to the natural log. So then this is just try to relate it, right? The size distribution. So on different variables. Okay. So this is just give you some ideas. Okay. So now, so if you have some aerosol, say number, surface, or mass distribution, right? So we try to say to understand some property, right, of this size distribution of your population, or we try to describe, right? Say describe your aerosol, say size distribution. So of course, I think you have some idea, right? So when we talk about the size distribution, right, or some data distribution, so we talk about some mean, variance, right, median, mode, something like this. So we're going to have a quick ideas, okay, to show you. So in case if you are interested to talk about the aerosol size distribution, right? So how you're going to calculate or to describe this aerosol size distribution. So of course, most of the time, so we're interested to look at the size, right? So we talk about the mean diameter, right? So that means that you're interested to look at the mean aerosol diameter, okay? So let's say now we focus on the number first. So therefore, when you talk about the mean particle diameter, right? So I'm sure you know how to calculate this. So we just present these in a way to using your aerosol size distribution function, right? So I'm sure you know how to define so-called the mean diameter, right, or mean value of your distribution. So now we just using the aerosol number distribution. Okay, so now you can see this is your aerosol number distribution function, right, times the diameter. Okay, and then you do the integration, right, for the whole range, and then you divide it by the whole range, right? This is, if you look at these, right, so this is your aerosol number distribution. So you take the integration, right, from zero size to infinity. Basically means you're looking at the total number, right? This is just your NT, right, the total number of your particle, right? So you basically you just divide it by distribution, right, and then divided by the total number, okay, of your particle. So this is basically just the equation, right? So we calculate the mean value of your parameters. Just to quickly remind you, so you can also do these, right? So for your surface mean aerosol diameter or your volume, okay? So because now you can just using the number. Remember, so most of the time for the aerosol studies, okay, so you can present your data, say in terms of the number, right? Number distribution. Or you can present in the surface area, right, distribution, and also the volume. So therefore, you can have the mean diameter, okay, in terms of, say, number, surface area, and also the volume. So therefore, if in case you don't do the number, right, so then you can use the surface area distribution, then this become the NS, right? So this is just for your information. So maybe just a quick show it to you. So now you are talking about the average, okay, surface area. So then now you use the function is the NS, okay. So you can also do the same things for the average volume, right, of the population. So okay, but just for the discussion here, so we just usually focus on the number, okay. But basically, just you change the function, right? Okay, for the surface area and also for the volume. And also another thing, or another parameter, right? So we always talk about is the variance, right? So the variance basically means that tells you the spread of your data, right? So therefore, the other thing is we call the variance, right? So I'm sure you have learned these in some of your mathematics classes. So we just show you in terms of using the aerosol size distribution, okay, data. So this is called the variance. Of our distribution, right? So when you say the variance, right, so remember, so we are looking at the deviation, right, or the spread of your distribution, right? Say around the mean diameter, right? So you need to know the mean diameter, right? So therefore, if you look at the variance, so how we calculate the variance. So if you remember, right, so for the variance, so you're looking at kind of the measure of the spread, right, of your distribution, say deviated, right, or different from your mean diameter, right? So and again, so then you divide it by your NT total. Right? So this is NT. So this is kind of the variance. So basically the variance, if you remember, right, so if you know the distribution of your aerosol, so you're looking at the variation from the mean. And also there's another parameter. So sometimes we're also going to talk about, so when we describe the aerosol size distribution, is we call the median diameter, right? So I'm sure you know the median diameter, right? So basically you talk about the diameter, right? Just which is below about just 1/2 of the particle, right? Or just 50%, right, of the particle. So therefore, for the median, right? So if you look at the median, and then you look at the accumulation, right? Or so that would be equal to 1/2, right? Because you are talking about 1/2 of your particle, right? Say lie below or above, right? So you talk about the 50%, right, of your total. So that means if you remember, so I'm sure you know this, right? So this is your accumulation, right? Graph. So this is your, say, 100%. This is the BP. So the median, right? The median diameter. So that means you are talking about 50%, right? So if you look at your cumulative graph here. Okay. So therefore, when you take the integration, say from 0 to your median diameter, right? So then that would be just equal to 1/2 of your total, right? Aerosol number. And also, one last thing is, or usually we don't use that this parameter that much or that often. Is what we call the mole diameter. Mole diameter, okay. So the mole diameter is a kind of you try to find the maximum, right, of your number distribution, or sometimes we call the local maximum of your number distribution. Okay. So that means in case it's a distribution like this, right? So what is the mole diameter is try to locate, right, this kind of the local maximum of your number distribution. And then to find this, we call the mole diameter. So you just to try to calculate the slope, right? And then you set try to equal to 0, and then try to locate this kind of the local maximum. So usually these are kind of like the property or some kind of the parameter, right? So we use to describe like the distribution of our aerosols. Okay. But one thing is that you can see, we just show you the way you calculate, right? This kind of a parameter. One of the most important thing is that you need to somehow have the function, right? You need to find a function to describe your aerosol size distribution. Okay. It turns out that if we have studied the aerosols, okay, we find that the log normal distribution so usually we find that the log normal distribution can kind of provide a good fit, okay, to our aerosol size distribution data. So in case that we study like the aerosols size distribution, okay, so you will find that most of the time, so when you try to plot your data, especially you plot in the log scale, okay, so you can try to fit the data, right, with some function. So you will find that we can always using this we call the log normal distribution, okay. So in case if this is the case, so I think you come across with this kind of log normal or normal distribution, right, in some of your statistic classes, right? But we just try to describe this or try to apply this to some aerosol population. Okay. So remember, because when, of course, I think you heard about the normal, right? Normal distribution. So the log means when you again, so if you look at the x-axis here, right? So you talk about the log scales, right? So this is kind of the log scale. Okay. So therefore, in case, okay. So let's say if we find your aerosol population. So let's say it's a log normally distributed. So then you can describe the function. Okay, so using this. Okay. So now let's say your aerosol population, right? Then is your data. Okay, is a log normally distributed. So you can just describe by using this function. Okay. So now this is the function. We call the log normal function. Okay, to describe the distribution or your aerosol population. So now you plot your x-axis. Okay, in this kind of a lateral log, BP, right? So that's where you put an E here. Okay. So now you can see you can describe this kind of a distribution. If you have log normal distribution, so of course you are not looking at things like this. But I'm sure you see the curve or graph like this, right? This is kind of the normal distribution, or we call some kind of called the bell shape, right, of your aerosol of your population or distribution here. But one thing is you can see is to describe this kind of log normal distribution function here. So you can describe by a few parameters, okay? So which is called the NT. So now we have defined this before. So NT here means the total aerosol number concentration, right? So in case that now we talk about the number here. The NT is the total, right? Aerosol number concentration. Okay. And also to describe or using this function, right? So you can see there's two other parameters. Okay, one is called this sigma G here. And then you can say, and also you can see this, we call the bar, this is the diameter, and then we put a G here, right? So you have this kind of a free parameter, okay, to describe the function here. So now we're going to show you so what's the physical meaning, okay, or the physical significance of these two parameters, this sigma G and also this dp G here, the mean dp and then plus a G here. So what's the physical insight or the meaning of these two parameters? Because to use this function, right? So you can see that you need to have this three parameter here. But one more thing is, if you remember, so most of the time, so we mentioned, right? So your raw data, so usually it's not in the lateral log scales or the log scale, right? But just I want to show you another way to present your data, right? Just using just the dp, but not in the log scales. So here we just show you, if you remember, so before we talk about this, so we can always correlate it, right? Or relate these two functions, right? So this is your number distribution, right? So you just plot in the dp. So this is the number distribution you plot, but this is a log, lateral log, right? dp here. So you can relate this one. So you can see somehow you need to change and then introduce this kind of the parameter here. Okay. So these are just to give you some examples. So in case you want to say to change, right, your variables. Okay, so you can come up with these ideas. Okay, but one more thing is the most important thing, like I mentioned, right? So we need to somehow have this kind of meaning, right? So what are the physical significance, right, of this three parameters? So this one is easy to understand. So this is just your total, right? Aerosol number concentration. So in case you're talking about the number, right? Then how about the other two? Okay, so we're going to talk about this. So now we want to talk about these two parameters. Okay. So now you have this kind of the log normal distribution function. Okay. So now we want to first to look at this we call the cumulative size distribution. Okay. Let's say so you have this function, right? This log normal distribution function. So now we're looking at this we call the cumulative size distribution. So that means you try to looking at, say, up to certain size. So what's the number of aerosols, right? So you have so up to certain number of size. Okay. So what I'm trying to do now is that if you remember, right, so we are looking at the cumulative size distribution, right? Say up to a certain particle size, okay? So therefore, when you're taking this, so you can just take this integration, right? For this function, we just show you, right? So you can take the integration from 0, right, to certain or to the particle size that you are interested, right? Okay. So I just change the star here, just to become just like a dummy here, right? So we just have the same function here. Okay. So therefore, you are looking at, say, the number, right? The number of your particles, say, up to a certain size, and then you take this integration, okay, using this function here. Remember, we are not using the natural log one, so therefore we are using this equation here. And then if you take this integration, okay, so we just skip the steps. We just show you the result. So we can find the detailed steps in the textbook. But if you look at the result, okay, I just show you the result. I skip the steps. So, but the idea is that for your cumulative size distribution, say up to a certain size, particle size that we're interested, will be equal to, this is NT, if you remember, NT is the total, right? Aerosol number concentration divided by 2 plus this NT also again is the aerosol total number concentration divided by 2. And then this is the error function, okay? So this is the error function. So it depends on this electron log dp, so the particle size that we are interested, divided by this bar dpg, and then you can see divided by this square root 2, and then this is sigma g, right? So this is called the cumulative size distribution function, NDP. Okay, so you get this function here. Okay. So if you remember, so for kind of this kind of the error function. So if you look at the error function, so you will find that the error functions. So you will see something like this, right? So say when you say approach the center will become 0. So we set the way from the center can be -1 and +1, right? So this is kind of the property of this error function. Okay. But now if you say we have this kind of the cumulative size distribution, right? So this is kind of the equation. So what we can do the analysis to try to understand. So what's the meaning of these two parameters, right? Okay. So first, so let's say if we just set our dp, okay. So say the particle size that we are interested. So we just say dp equal to this dp bar, right? Take the g. So this is a dpg, take the bar. So if you set this, right, the particle size that we are interested is just equal to your dpg bar here. So now you can put this into this equation, right? So now you will see that if your dp here just equal to the dpg bar here, so this term will become 1, right? So this will become 1 because you just if you set this term. Okay, so I just set this dp equal to the dpg bar here, right? So therefore, this will be the same, right? So that will be equal to 1. So if you take the electron not 1, so that will become 0, right? So the whole term will be 0. So therefore, your error function here will become 0, right? So therefore, if I set this, so your error function, this term will become 0 because the natural log 1 will become 0, right? So therefore, the whole term will become 0. So therefore, your error function will be equal to 0. And then if you remember, I just show you the graph. So when you say for the error function, if set equal to 0, So it will give you also 0, right? So now if this error function is 0, so that means this term will become 0, right? 0 times this, so therefore this will also become 0. So now you can see that the result will be so if I set my dp equal to this dpg bar, okay, I do this in my cumulative size distribution function here. So you will find that that will be just equal to nt divided by 2, right? So if this is n2 divided by 2, so what's actually the meaning of this? Say the dpg bar here. So this is just the median diameter, right? You see the point, because the median means, right? So when you say median, right, if you remember, so we just show you, right, the median is just the 50%, right, of the particle number, right? So therefore, you can see from this analysis, right? So you will find that the physical meanings of this dpg bar here is just the median diameter. So therefore, if we are looking for a physical meaning of your dpg bar here in your log normal distribution function, okay. So then you will find that the meaning of this dpg bar is just the median diameter. Are you okay with my argument? So we are not. I think that the message here is this bar, right? So you think that is a mean. So remember, this is not the mean. It's the median. Okay. So this is different. So I think the things that we highlight here for you is because most of the time, in case you forgot, you will think that this is just the mean diameter, right? But I just want to show you that if you're talking about a log normal distribution function, okay, this dpg bar here, so this is called the median diameter of your aerosol distribution, okay, of your aerosol population, not the mean diameter. Remember, I just say I want to highlight it's not the mean diameter. So what I show you here is the median diameter. Are you okay with this? So this is just I want to highlight is the median diameter. Okay, so now we're going for the other one. So we go for the other one. Okay, so now we want to look at this kind of the sigma G here. Okay. So what's the meaning? Okay, so let's say let's consider a diameter, say is called the dp plus is the sigma, okay? So I just try to follow the notation we use in the textbook. So what's the meaning of this diameter, okay? So this is called the sigma G will be equal to this dpg bar times this sigma G will give you the diameter that I'm interested here, okay? So this is just by definition, okay? So I'm just interested, say we can also argue this. We can just present the other way is this diameter. I try to find a diameter. Is we call this kind of, now you know this is the median diameter times this sigma G, okay? So now we can also do the same analysis, okay? So now you define this dp plus this sigma, right? Okay. So now you know that this is equal to the we can now know this is the median diameter times this is sigma g. So what we can do now is you can also substitute to this cumulative size distribution function, right? So if you put this here into this term, so now, right? So now you need to have times this sigma g, right? Because I try to substitute this, right, into this term. So now your dp become your median diameter times this sigma g. So now if you substitute this, so you will find that at least you will cancel out, right, this median diameter. And then you will have this lateral log, right, lateral log, this sigma g on the top. And then say you will divide it by the square root of 2. And then you still have this lateral log sigma g, right? So this is when you do this substitution. So therefore, if you cancel these two, so now your error function will become 1 over square root 2, right? Are you okay with this? So now this your sigma, sorry, your error function will become 1 over square root of 2. So therefore, if I substitute this, that's a 1 over 2, okay? So now you can put in your calculator or your program, and you can calculate the value for, say, when error functions will be equal to 1 over square root of 2, right? And you can calculate this term, and then you will find that that will be equal to so that will be equal to just a 0.41, so 0.841 times your NT, right? So what's the meaning of these, right? So more important is what's the meaning of this? So basically now you are looking at kind of a ratio, right? So you're looking at some ratio of a diameter, right? So let's say 84%, right, of your population, of your particle population, right, will lie to these we call the median diameter, right? So because when you time this median diameter, right, you time this sigma g, right, and then you get a new particle diameter, right? Say this is the dp per sigma. So you will find that so with these, right, this diameter, so 84%, right, of your aerosol population, right, will lie to this, right, will below this value, right? So therefore, actually, this sigma g is kind of the ratio of the diameters. So let's say below. So more precise means it's the 84.1% of the particle, right? So lie to this, we call the median diameter. So basically, they will also give you a name. So later we're going to show you. So, but what's the meaning of this? So if you know this is 84%, right? And also we are talking about some cumulative size distribution. So what's that means of your? So now you know, right? So this is your median diameter, right? Will give you 50%. So I try to find a median diameter, right? And then I time this sigma g. So then I get a new diameter, right? Say by definition, this is your dp plus this sigma, right? So what's that mean? So that will give you 84.1%, right? So this is the minute. And then how you get this number, right? dp plus this is sigma, right? So that would be equal to your median diameter, right? So of course, here we use this dpg bar times your sigma g, right? So then that will give you this dp plus sigma, right? And then if you get this diameter, okay, using this equation, so that will say this is about 84.1%, okay, of your NT, right? Does it make sense? So therefore, this sigma g, we also give a name for this. Is we call the geometric standard deviation. So this is also give you some idea about kind of the variance of your population, right? But we just give you more idea or the physical meaning, okay, in terms of aerosol population. And also the name to be called this is called the geometric standard deviation. Okay. Are you okay with this? So I'm sure you get some of very similar or the same concept before. Okay, but here we just try to apply this when we say or when we talk about some aerosol population. Okay. Are you okay with these two parameters? This is called, now you know this is the sigma g's. We also give a name called the geometric standard deviation. And this we call the dpg bar here. So now you know that this is not the mean diameter. Remember, this is not the mean diameter. It's called the median diameter, right? So we show you here. So do you have any questions so far? So basically, this geometric standard deviation is also like the variance, right? So give you some the spread of the data here. So if you are okay with this, so let me see. I want to save some of these equations. How about this? So remember, so of course we show you the log normal distribution function. Okay, so of course you can also always apply this to your different types of aerosol population. Okay, but one thing is we always emphasize two cases. Right? One is called the monodispersed. Monodispersed means that you only have a single particle size. So therefore, in that case, so when we say or when we talk about, we call the monodispersed aerosol population. So we know that you don't have this kind of the variance. So the sigma g equal to 1. Okay. So in case your aerosol population is a lot normally distributed. Okay. So but if you say this is not just a single particle size, so therefore we have a term called the we call the monodispersed aerosol population. So now you know that your sigma g will be set equal to 1. And then if you have aerosol size distributions most of the time, so we call this polydispersed. Okay. And also, so most of the time, so you want to have a distribution like this, right? So I think you remember, right? So you try to set a different range or boundary, right? So you can find that that will be equal to about 67%, right, of your particle. So in case we are talking about a aerosol population, right, and also it's a not normally distributed, right? So to look at these two values, the size, that will be equal to if you say you can find your median diameter, if you say time this sigma g, or you can have your median diameter divided by your sigma g, and then if you look at your aerosol population within these two size range, within these two particle size, so that will give you about 67% of your particle population or your aerosol population. This is always we say that if you're interested, say looking at about 67%. So remember, you usually when we say it's plus or minus some variation or standard deviation, remember we are not saying plus or minus. So now you just need to be times or divided by your sigma g or your geometric standard deviation. Okay. So therefore, in case this is about 67%, if you're interested to look at say 95%, right? So that means in this case, so you are talking about the square. Okay. Okay, so you are looking at the size range here. So if the size range from this your median diameter divided by your geometric standard deviation taking the square to, so this your median diameter times this sigma g to the power of 2. So you're looking at this particle, right? Size range. So that means I use the red dot here. So now if you just have this red one size range, maybe I draw the line. So that will give you 95%. Okay. So this is a bit different, right? So when we say you're using the standard deviation or things like this, so but just to give you the idea, so in case you try to find this, say 67% of your aerosol population or 95% of your aerosol population, right? So you're looking for the size range. Okay, so this will give you ideas. So any questions so far? Okay, good. But again, so if you have any questions, so feel free to stop me. Okay, so one more thing is we talk about, now you know this sigma g is called the geometric standard deviation, and also this dpg bar is what we call the median diameter, right? So most of the time, so people are interested in looking at the mean diameter, right? We still are interested in looking at this, what we call the mean diameter. So remember, so this is the mean diameter, it's not the dpg bar, right? So this is the mean diameter, dp. So let's say if you have your aerosol population is also a log normally distributed. So now you're looking at a mean diameter, right? So therefore, you go back to the definition. This is the mean diameter. So you're talking about 0 to infinity, right? And then you have the dp. So this is just the by definition, right? So this is your number distribution function times the diameter, right? At a given size. And then you take the integration from 0 to infinity, and then you divide it by this term is just your total, right? Aerosol number concentration, NT, right? So we show you before. So now you see, now you know the function, right? So now you know the function. You say log normal distribution function here. Okay, so therefore, if you're doing this, so basically, you just substitute the function into this integral, and then you take out the constant. And also, you know that you can cancel this NT, the N total, right? The total number of aerosol concentration. Therefore, you don't see the NT here. And then if you solve this equation, okay, then you will find that your mean diameter so the mean diameter, okay, of a log normally distributed aerosol population, so will be just equal to your median diameter, right? This is the BPG bar, and then you times this exponential, and then you need to look in for the variation, right? The variance, right? Or the spread of your distribution. So therefore, if you take the natural log square, this is your sigma g, right? Your geometric standard deviation, and then divided by the 2 here. Okay. So therefore, you can also see that your mean diameter, right, is also depends on your median diameter and also your geometric standard deviation. Okay. But the one thing is, so why we want to spend sometimes to talk about this aerosol size distribution and also talk about the log normal distribution function is again because most of the time, so when we look for our aerosol distribution data, so you can again, so this is go back to at the very beginning, right? It's because your size distribution data can always be good fit, right, by some log normal distribution function. Okay. And also important thing is that you can see here, right, to describe this aerosol population. Okay. So of course you can use the log normal distribution function, and also you just need 3 parameter, right? So you can use a 3 parameter to describe like the property, right, of all your distribution of the function. So that means that you just need to know the NT, okay, your sigma g, so that means that this is your geometric standard deviation, and also the median diameter, right? So you just need these 3 parameters, and then you can describe your aerosol population. And also, if you're given your data can be fit by a log normal distribution function, right? Kind of the property of your aerosol population, say if you're interested to look at the mean, the median, the spread, okay, or if you want to say within a certain size range, so how many particles, right, within a certain size range. So you can easily calculate, right, just using 3 parameters here. So that's the reason why so people want to look at this we call the log normal distribution function for the aerosols population. Are you okay with this? So therefore, for those who study the aerosol science, so when in case you talk about the aerosol population, so most of the time you talk about this called the log normal distribution function here. So any question? So we just kind of present in a way that in terms of the aerosol size or aerosol population for you. And one more thing is, remember, right? So we focus on is we call the number distribution, right? So we talk about the number distribution. So of course, if you also plot your data, say in the surface area or the volume, also most of the time, so you will find that the population, the aerosol volume populations or your aerosol surface area population, they will be also log normal distributed. Okay. And also, people find, we don't go into the details here, but if your number distribution is a not normally distributed, okay, so then you plot your data, okay, in terms of surface area or the volume, they will also be not normally distributed, okay? And then they will have the same geometric standard deviation. That means they will have the same sigma g. But the only thing the difference is just the median diameter. Okay. So I think there's a nice discussion in the textbook. But I just want to highlight here. Because this is just some statistics, so we don't go into details. But just want to, for your quick references, is in case if your number distribution, okay, is what we call the log normal. And your surface distribution or your volume distribution will be also log normal. That means your NSDP, NVDP, so would be just also log normal. And also, if you look at the distributions, so one thing is that they will have the same sigma g, okay, they will have the same geometric standard deviation, but of course, their median diameter would be different, right? So you can also relate it to these. So the idea is if your aerosol, okay, population, in case in your number distribution is a log normal, so like I mentioned, so the surface area or the aerosol surface area or the volume distribution will also be log normal. So they will share with the same geometric standard deviation, but of course you will see they will have different, we call the median diameter, right? So this is the surface, this is the volume, and then you can relate it to their number, right? So this is the median diameter, right, for the number distribution. And you need to check with this, we call this also depends on the sigma g here. So for the surface area, so that will be plus a 2 times the lateral north square, this is sigma g. And then for the volume, it will be 3 times the lateral north square, okay, sigma g here. So therefore, this is the differences, okay. So I think this is just a statistic, so we don't go into the details. I just give you the information. But one more thing is I want to highlight here is, of course, I always tell you your aerosol population most of the time, so it can be well fit, right, to some log normal distribution. But I'm sure when you do some literature reading, right, so you will see most of the time, so people can have a multiple peak, right? So for your aerosol, say number distribution, okay. So in that case, so what we try to do, or most of the time we try to do is, in case if you see multiple peaks, so you can just say you can fit your data, okay, with different, we call the log normal distribution. Okay. So if you see multiple peaks, maybe in this case, so you can just fit with 2 different log normal distribution functions. And then you can just sum them up, and then you can just describe your data. So this is most of the time we process the data here. Okay. Because the idea is for the ambient aerosol, in case you have interest to look at the ambient aerosols, so most of the time you will see multiple peaks. So in that case, you don't just use a single log normal distribution function that you can describe by a combination of different log normal distribution functions in this case. So in this case, just the two, right? So you have one here, and then another one here, right? It's just a combination of 1 and 2, and then we'll give you the overall population. Does it make sense? But the overall, I think the main things that we want to spend some time to talk about this is just want to try to apply this kind of the normal distribution or log normal distribution you learn from your statistic classes or mathematics classes to some aerosol population. Okay, so we try to just describe this, okay, for aerosol population. So just to quickly remind. And also the good thing is that these functions is always can be applied to your ambient aerosol data and also your chamber or laboratory generated aerosols data. So that's why we just want to spend some time here. So do you have any questions so far? Okay, then if not, so now we give you some idea about the aerosol size distribution, right? So now you have the idea is that we can, most of the time, so we can describe this aerosol population, right, using the log normal distribution function. So again, I just want to, from time to time, I want to remind you that most of the time, okay, so remember, so when you talk about the aerosols size distribution, so your x-axis, okay, so most of the time is the log dp, okay, with the log scale. So that's why we call the log normal distribution. Okay, so this is, and then now you can see that if it's a log normally distributed, so you can well describe the aerosol population properties or distribution just using slit parameter. And just to highlight again, so these, okay, if you see this bar, remember this is not the mean diameter, okay, it's the median diameter, right? We show you this is the median diameter of your aerosol population, and this is the geometric standard deviation, and this is your total aerosol number concentration. So any questions so far? So then if not, after the break, then now we're going to talk about, because most of the time, right, so we are not talking about a single size, right? So monodispersed. So monodispersed means that you only have one single size, right? Polydispersed means you have distribution. So then we want to, after the break, so we're going to say if you have a condensation or evaporation, right? So how your aerosol population will change with time, right? Because you have different size, so how the aerosol size distribution will change, say when you have an evaporation or condensation process. Okay, we're going to talk about this, and then we'll go back to using some of these equations here. Okay. So any question? Okay, if not, then let's take the first break here. So let's take a 10-minute break, and then we'll come back at 12:43. Okay, so let's take a 10-minute break. In case you have any questions, so feel free to ask me during the break. So maybe we can just resume the class. So, but before we start, so do you have any questions from the class? Okay. So before we talk about the condensation, I want to just have some discussion about your term project and also your literature review. Just to spend a few minutes talk about your term project and also your literature review. So remember, so for the UG, right? So if the UG students, so you need to submit your term project, individual term project, together with your presentation, and also for those who are the PG students, so you need to submit your term project, presentation, and also a literature review, right? So of course we have been covered many topics so far. In case you have any problem or difficulty to identify, okay, your title for your term project and also your literature review, so feel free to talk to me, okay? And also I just want to remind you that we're going to send you the guidelines in more details later, so we're going to post it. But I just want to let you know for the term project and also your literature review, So you're going to submit, okay? There's the due date, right? So I want to give I think most of our students are in the class right now. So I'm going to set the due date, the submission deadline. So will be May 11th, okay? It's a Wednesday. Are you okay with this? So that means just about 1 month from now. Okay, 1 month. So you have about 1 month to finish your term project and also your literature review and also your presentation. Okay, are you okay with this? So 1 month from now, and just for the term project and also the literature review. So I assume you're going to for kind of the content, or if you're concerned about the number of pages, right? So I would suggest 10 to 14 pages for your term project and also your literature review. So about 10 to 14 pages. Of course, just the standard, say 1.5 spacing and font size 12. Okay. And then that will be include some essential figures, okay, but exclude the references. Okay. So 10 to 14 pages, okay, for your term project and also your literature review. And also the deadline will be 11th of May. Okay, it's a Wednesday. Are you okay with this for the class? Okay. And then the last thing is to discuss your presentation. Okay, so remember, you also need to submit a presentation, a video tape presentation. You can submit on using the Zoom. So the presentation or your recorded presentation is about 15 minutes. So you're going to send us your videos together with your PowerPoint. So you can upload these to the web box, okay. And also the due dates will be the same, okay. So it's also May 11th, okay. For both your presentation, your term project, and also your literature review. So 1 month from now. Okay. So any question or concern or comment from the class? Are you okay with this arrangement? Any comment? So in case you have any comment, I think it's the best time for you to express your concern. If not, then I assume we are okay with this arrangement. So the only thing is, in case that you're still struggling or try to identify your term project, the title for term project, and also literature review, so you're welcome to talk to me, okay, or the TA. So if you want to seek some advice, okay. Okay, right? So, and then if you are okay with the dates and also kind of like the content, the number of pages, and also the way you upload your videos and your PPT, so then we'll send you the details later this week, okay? So you have about 1 month from now, okay? Good. So now we're going to continue, okay, to talk about some kind of the dynamics of your aerosol population, say now due to the condensation. So of course, you can also apply these for evaporations. So because in this class, we just talk about say using the condensation, okay, and then to see how you will change, okay, your aerosol population. Right. So we're looking at, so if there's some condensation process happen, so assume in case that at the very beginning, so you have aerosol population is not normally distributed. So what will happen, say, if you have condensation or say evaporation? So what will the kind of the change, right? in this aerosol population, or their size distribution, surface distribution, or the volume distribution. So we're going to talk about this. So that means that we're going to look at, say, the rate of the change, right? So we're looking at if there's some condensation, right? So what is the rate of the change, say, in the size distribution? So I think we have discussed when we talk about the aerosol dynamics, the single aerosol particle, right? Dynamics. So we talk about the condensation. Okay. So let's say if in this case, so let's say if we have a condensation, and let's say now we talk about the condensation. So how the condensation, right, change the, say, the diameter of a single particle first. Okay. So let's say we try to look at, say, the rate. Now let's say we talk about the condensation. We first are looking at a single particle first, okay, and then we're going to talk about a population or the entire population. So let's say we talk about condensation for a single particle. So let's say we have a certain diameter, right? So let's say we have a diameter dp. Okay, so we want to look at the rate of condensation. So I think we show you this, we kind of show you the equation before. So that will be related to so this is just the equation, right? So I think we have discussed this equation before. So let's say you have a condensation, okay, to a single particle of the diameter dp, right? So this will be the rate, right, changing your particle diameter, or we say the mass, okay, of this. So this will be related to the 2 pi times the dp. So remember the dp is the diameter of your particle, and then you're looking at the diffusivity of your species, right? So let's say you have a species I, right? So diffuse to your particle. So you're looking at the diffusivity, right? Or this is, we call the diffusion coefficient of your species di. So this is dp is the diameter of your particle. di is the diffusivity, right? Or diffusion coefficient of your species I in the gas or in the air. Mi is the molecular weight or the molar mass of your species I divided by the RT. So remember, so when we talk about the aerosol dynamics, so that will be depends on whether we are in the continuum regimes, kinetic regimes, or kind of like in between, like the transition regime. So you need to do the corrections, so, right? So this is called the Nusselt number. If you remember, the Nusselt number means that you're looking at the ratio between your Feynman part diameter to your particle diameter, right? And then this alpha is the accommodation coefficient. So because if you remember, when we go down to small molecule or free molecular regime, kinetic regime, so now the behavior of your particle is, right, become more like a gas molecule, right? So every time when you have this kind of collision, right, so condensation, they are not always stick onto the particle, right? So then we need to correct for this sticking coefficient. And then this is just the driving force, right? This is due to the concentration gradient, right? So of course, this can be related to the partial weight pressure, right, of your species in the gas phase, and then to the surface, right, weight pressure. So this is a kind of the equation, right, we showed you before. Okay, just for these cases, okay, we just simplify this. Of course, we know these functions. This is a correction factor, right? So let's say for this discussion, simplified discussion, we just assume this is a continuum. So that would be this will be set equal to 1. Okay, so we just set this. But of course, we can relax this assumption, right? So later. So, but in this case, we just assume it's equal to 1. So therefore, if you look at this equation, okay, so I think we have discussed this before. So you are talking about the rate of condensation, right? Kind of the mass change to a single particle of a given size, dp here. Okay. So therefore, you are looking at, if you're looking at this equation, so we are also looking at some kind of a mass change, right? Right, because you have some species, say, let's say, condensed to the particle, and then you have some mass change here. But now now we are not just looking at a single particle, right? So we're not looking at a single particle. So we are talking about our aerosol population, right? So therefore, you need to apply these to an entire population. So now we want to look at, say, we are not just looking at a single particle, right, or a particle with a single size. So we are looking at a aerosol population. So therefore, we have this called the RC. Oh, forgot to measure R is kind of the rate of condensation. Okay. Here. So if you say this is say we put another C here, means we talk about the rate of condensation to the entire population. Because we want to look at is the condensation, right, to the whole population, like aerosol population. So you can by doing this, right, if you know your aerosol distribution, and also this is kind of the rate of condensation, right, to a given particle size, RC. So we can do this, right? So your RCC will be equal to, of course, you're taking the integration, right, for your whole particle population. So let's say you can find a population. This is the distribution, right, of your population or aerosol population. So this RC, of course, this is the rate of condensation to a given particle size, right? dP, so it's a function of dP, right? But because it depends on your particle size, with different size, so you have different rates of condensation, and then you just times this your size distribution function, right? So given this, okay. So, but before we want to continue, so I just want to play around with the unit to make sure, so we're on the same page. So what's the unit we're talking about? So remember, so this RC, like I mentioned, right? So you're talking about a condensation of the species to your particle, and then you change the mass of the particle. So therefore, this RC, right, is the rate of condensation to a particle. So you can kind of have a unit, say gram, because I'm looking at a certain particle per time, okay? Because I'm looking at a single particle, right, at a different size. So therefore, you're looking at the mass change of a given particle at a given time. And then this is your particle size distribution, right, function. So therefore, you are looking at the number, right? So now you're looking at the number of your particle, right? So number concentration of the particle at a given size, right? Size range. So for the particle size, you're usually using the micron, and then this is your change of you're looking at the size speed, right? The size range here. So therefore, the whole thing, if you look at these, is the rate of the condensation to the entire population. So you will have the unit. Okay, so gram per cm cube per second. Okay, so that would be the unit for this rate of condensation to your entire aerosol population. Are you okay with this? Because this RC, you are talking about the condensation to a single particle, and then you times your number distribution. Overall, will be the gram per m cube per second. Okay, so this is the unit for the rate of condensation to your entire aerosol population. So then you can just take the integration from 0 to infinity, right? So you're looking for the whole population. And then if you can also substitute this, right? So this, of course, is a function of dp here, right? And then you can just put this into here, and then you have this function. But one thing is, like I mentioned, right, to simplify our discussion. So first, let's say we set this f equal to 1. Okay, so let's say we assume this is a kind of in the continuum regime. Okay, just to simplify our discussion, but of course, we don't need to make this assumption, right, when you do your calculation. But just on the whiteboard, I just assume this is equal to 1. So I don't need to write down this every times here. So if you look at this RC term, so most of the dams, the parameters are constant, right? So the only thing is your dp, right? So this is the dp will change. But your 2 pi, your diffusivity, that means your diffusion coefficient, your molar mass of your species, this is just the gas constant temperature, right? This is just the vapor pressure difference, right? Concentration difference here. So if you just substitute these terms, the RC into here, right? Then you will find this RCC. So what I try to do now is I just I take all this. This is because this parameter just like a constant, right? So I take the integration. So I can take this out. This term, this is 2 pi times the diffusivity of your species in the gas, and then this is the molar mass or molecular weight of your species I, and then this is RT, gas constant, temperature, pressure gradient, and then you take the integration from 0, and then remember you have a dp, right? So therefore, your dp will also go inside here. So that's why you have the dp here, your particle diameter, and this is your distribution function. And then you take the integration, right, from 0 to infinity, right, to look for the whole population. But one thing is, if you look at these terms, so what's the terms here? Okay. So if you remember, when I take this integration, just to recall, if you want to define some kind of we call the mean diameter, right? So what's the mean of the mean diameter? dp mean will be equal to 1 over nt, right? Take the infinity. Right, so you can see this is your how we define or how we calculate the mean diameter, right? So the mean diameter will be equal to 1 over the nt. Nt is the total aerosol number concentration, and then you take the integration of dp times the size distribution function right here. So you can see this term just equal to this term, but you need to times the nt to the other side, right? I just put the other side here. So therefore, this term, if you compare this term to this one, so basically, if you take the integration, right, from 0 to infinity, this is dp times your size distribution function, dp here, right, this term. So that means that if you put this term on the other side, right, the integration for this term is just equal to your mean diameter times the nt, right? So therefore, if you just agree with this, okay, so now I can just substitute this here, right? So now you can see here. So now you can kind of see like the rate of the condensation to a entire the aerosol population, right? So in terms of the units, kind of the gram per cm cube per second will be equal to 2 pi times this is just the diffusivity of your species I times the molecular weight of the species I divided by RT, vapor pressure difference, right? And also just the times this is kind of the mean diameter, right? The mean diameter of your aerosol population, and then times this NT. NT is your total, right? Aerosol population here. But remember, so to do this, of course, we assume F1 is equal to 1. So we are talking about a continuum regime, right? So this kind of this equation, okay, can also give you some idea about the rate of condensation, okay, to an entire population. But of course, we apply this when we talk about in this we call the continuum regime, right? So of course, this is because if you're not continuum regime, then this is also a function of dp. Then your integration become much more will become more complicated. But here we just simplify this to a continuum regime here. Are you okay with this? Okay. So now this is give you some idea about the rate of condensation to the entire population. But sometimes is we also want to know. So if you have say a monodispersed. So for example, I only have if my whole aerosol population just have a single particle size, and then if we have also have a say compared to say with a polydispersed. So we want to look at say the condensation rate. Okay. So what would be the difference between if you just have the monodispersed aerosol population and also compared to a say the polydispersed aerosol population? So what would be the rate differences? Okay. Because most of the time, so of course, we spend quite a lot of time, say, we're looking at a single particle or a single particle with a single size, right? But again, so most of the time, so we have this kind of the polydispersed population. So therefore, we want to say, we want to compare, say, the rate of condensation. So let's say to a monodispersed and also polydispersed particle. Okay, just like I mentioned here, right? So this is the monodispersed, right? And then this is polydispersed. But to compare of these, of course, you know, they can have different properties, okay, to have a more meaningful comparison. So let's say we assume they have some kind of some same total property, okay. Let's say if you assume this two distribution, right, the monodispersed and polydispersed population have the same, some kind of same total property. So in this case, so let's say we assume you have the same, so let's say the same number of aerosol NT, the total aerosol number concentration, and also the volume. Okay, so let's say you have the same volume. So now we want to see the rate, okay, condensation to a monodispersed and polydispersed population, and then to have a comparison. Okay, so let's say we assume this two distribution of this two population have the same. This is called the total number, okay, total aerosol number concentration, and also they have the same total aerosol volume, okay, VT here. Okay, so let's say we look at for some polydispersed aerosols. Polydispersed aerosol. Again, so we just learned that for polydispersed aerosol, so assume this polydispersed is we call the log normally distributed. Okay, it's a log. Right, so it's a log. So if by doing this, then you can have described by the function, right? So you can have the log normal distribution function. So I just quickly. Right, so if you remember, right, so if you have your polydispersed, okay, aerosol population, if it's a log normal, so you can describe by this equation. I just have to write this equation for you, and then you can describe this polydispersed population using just the NT against the NT is the total aerosol number concentration, and then you need to also know the sigma G, right? This is called the geometric standard deviation, and also this DG. The dpg bar. So now you know this is the median diameter, right, of your aerosol population. So you can describe your polydispersed population using this log normal distribution function. So then what we can do now is because this is a log, so we can have this function, right? You can put into this term here, right? So now you have a function for your aerosol size distribution, right? If this is a log normally distributed. So if you're doing this, okay. So now again, so this is the equation, right, for the rate of condensation to an entire population, right? So this is always you can use this. So this is kind of the rate of condensation to a single particle of a given size. So this is your aerosol size distribution function. This is your dp. So let's say if you assume your polydispersed population, right, is a log normal, then you can substitute this into this term here, right? And then you do the integration. Okay. Are you okay with this? So if you are okay with this, so you just take the integration. So basically what we are doing is you just substitute these terms to here, right? So because you can just substitute this term here. And remember, so these terms is kind of a constant, right? Of course, the dp you need to go into your bracket here. So by just doing this, okay. So let me just show you the substitution. So after the substitution, okay, so basically we just do the substitution into your equation here. And also just want to define a term A here. So A is kind of the out. Just want to define this term. So because this is a constant, so we just define A to be equal to So A is just from your RC. So this is some constant, right? Because this is the RC terms. Okay, so it's a kind of a constant. So therefore, I just group all these terms become called the A. I just follow the notation in the textbook here. Okay, and then you just take the integration. Okay, for your function here. So this is just the terms. So remember, because you have this 1 over dp, and also you have a dp from your RC term. So therefore, you come up with these two terms here. But turns out you can cancel these two terms out, and then just do this integration here. So the overall, the whole thing is just nothing fancy. We just substitute the one we learned from the RC, the condensation rate, okay, to a single particle with a given size, and just group them as a constant. And then this is just your function. Right now, you know the function is that this is called the normally distributed function here. And then if you're solving this equation, okay, so now you will find that if you just solve this, okay, if you solve this equation, okay. So therefore, for a polydispersed aerosols, okay, if you're solving these equation, okay, so then you will find that that will be, this is the rate of condensation to the entire population, right? We times this A is a kind of a constant from the RC. That means the rate of condensation to a given single particle. And then times this we call the median diameters. Okay, this is the dpg bar. And then you times the potential. And then you be related to this called the lateral loss square. This is sigma g is called the geometric standard deviation of your aerosol population divided by 2 times the nt here. Okay. And then this is the equation, right? For the rate of condensation to an entire population for a polydispersed right population in this case. So this is your RCC. And then you can also compare to the one we just derived. Right, so this is just the terms. So we just derive for the monodispersed, okay, for these two. But now you can see, of course, you can do some comparison here, but there's some terms are still differences, right? So we can just want to try to say, if you want to take the ratio, compare these two. So you can want to see, because you can see the term here. So you use this kind of the mean, a median diameter. So this is the mean diameters, right? For monodispersed is polydispersed. So first, we also want to do a few more steps, given because we can assume you have this, we call the same total property, right? So let's say you have the same aerosol number concentration and also the aerosol volume, right? So then we can do one more step to compare these two. So this is a polydispersed. And then this is called the mono. Okay. So because these two distribution, right? So we have the same volume and the same number concentration, right? So let's say you have this volume. This is your total aerosol volume. So how we can calculate these? So if you remember, right? So this is your total aerosol volume. So we'll be just looking at your aerosol number distribution function, right? And then you times at a given size, you're looking at the volume at a given particle size, right? So therefore you have this pi over 6 times dp to power 3, right? And then you times your aerosol number distribution function. So that will give you, right, the total aerosol volume, right? So if you take the integration from 0 to infinity. And also, like I mentioned, so now we know this is this aerosol size distribution is a log long, right? So you can also have a function for this, and then you can take the integration. So then if you solve this equation, so you will find that so because this function, this aerosol number distribution function is a log normal distribution, right? So you can just put this in, and then you do the integration, okay, together with this pi over 6 dp to power 3. So you come up with this, your aerosol total number volume will be equal to pi over 6 times your NT times your median diameter to power 3, and then this potential. Okay, and then you have this 9 over 2 times this lateral log square, and then your sigma g. This is sigma g is your geometric standard deviation of your aerosol population. So now we want to kind of relate these, right, with these terms. Okay, so therefore we can just apply this. So what I try to do now, I just try to put this median diameter, right, to power 3 to my left hand side. I just take the width, right, to power 3, and then you just rearrange this equation. So I try to find an expression for my median diameter, right, in terms of my V total, N total, and also your sigma G here. Okay. So then I can have this expression, right, for my sigma G, my median diameter. Okay, or we can say this is dpg bar. So I can substitute this, substitute this into this term here, right? So I can substitute this into here. So if I substitute this this term, and also one more things I can do. Maybe let me just show you the result. Okay, so what I'm do now here is I just substitute these terms into here, and then just rearrange the equation. So now you can find an expression. It's just to become an A times these terms, and then exponential, and then because minus natural log square sigma g, the geometric standard deviation of my aerosol population, and then times the NT. So these are the LCC, right? The rate of condensation to the entire population, right? For my polydispersed aerosol. Okay. So now I want to have another term here. So this is LC if I'm a monodispersed. So if you remember, for a monodispersed particle, right? So that means I only have a given size, a single size, right? So then you can also argue, right? My median diameter, okay, just the total volume, right? Divided by the number, concentration. Because you can see this median diameter, just the diameter we have, right? And then if you just times the volume, right, of that given size, and then times the NT will give you the total aerosol volume. So if you just rearrange this, so you will also get the mean diameter, right, for a monodispersed will just be equal to this 6 times this VT, your total aerosol volume, divided by the pi, and this is your total aerosol number concentration. And then you take the square root. Because you remember, right? This is just your dp time, and then you times your, right? So take the cube. And then you times the NT, right? Because you only have a single size, so this will give you the VT, right? So the total aerosol volume, just because every part has the same volume, right? That's just the mean diameter. So you just have the same thing here. Okay. So therefore, if I put this into this term here, so you also getting this term. Okay, now you can see that if this two size distribution have the same property, same NT and VT, okay. And now this is the top one is for the polydispersed, the bottom one is for the monodispersed. Assume you have the same total property, right? So these are these two. So if I take the ratio of these two, so you will find that I don't need to worry about the A. This term will also cancel, right? And also the NT will also cancel, right? NT will also cancel. So now you can see if I compare the rate of the condensation, okay, to two populations, one is the monodispersed and polydispersed, okay, with the same total property. So the conclusion will be so in case in our discussion, remember we assume these are two populations with the same total property, means the NT and the VT are the same. So you will find that the rate of condensation, right, to a monodispersed population will be equal to the rate of condensation to your polydispersed. This is called the polydispersed population. Time this is potential, okay, will be just a natural north square sigma g. Okay. But one thing you can also look at the equation here, you can find that, of course, if this will become equal, right? So let's say if my sigma g set equal to 1, okay, so they're basically the same, right? Because now become a monodispersed also on your right hand side. But these terms is always larger than 1. If you look at this term, it's always larger than 1. So that means that in this case, okay, so we can argue that the monodispersed, okay, the monodispersed population will have a faster condensation rate than polydispersed, okay, population, right? Because this term is always larger than 1. So therefore, overall, your monodispersed, okay, population, okay, will have a faster condensation rate, okay, than the polydispersed. So assume you have the same NT and VT in this case for discussion. So do you have any questions so far? Because of course you can see some will be faster, some will be slower, okay, for your condensation, okay, in the polydispersed, but overall, so that will be determined by this sigma g, right? So kind of the spread of your distribution. Of course, you set your sigma g equal to 1, that means just now your right hand side is also a monodispersed, so they will be equal, right? That would be the same. So this is just I want to have some quick ideas. Of course, we set some special case here, but just to give you some sense, because remember your condensational rate depends on the size, and then you compare the overall. Okay, so now I think the main message is if you compare a monodispersed to a polydispersed, so one thing that we want to concern about, of course, the aerosol property, right? The total aerosol properties, NT or VT or surface area increase. But more important is also the spread of the population, right? Will also affect your overall condensational rate or evaporation rate. So this is just give you some discussion here. So any questions so far? Okay, so now we want to continue. Okay, so it's a kind of we want to look at say the dynamics of some of the population. Because of course you can see here. So now we just compare the rate of condensation. Just the overall, if you remember, right, the RCC here is looking at the kind of the mass change, right, to your population. Okay, but one thing is when you have this condensation, right, your size distribution will also change. Remember RCC, if you remember the unit we discussed, right, is a kind of the mass, right, per volume per time, right. So you're looking at so how the mass of your population change with time. But if you have this kind of a condensation, right? When you do the condensation, like at the very beginning, right? This shape, right? If this is your size distribution, right? The shape of these will change, right? With time due to the condensation. So therefore, we want to derive a equation, okay, to describe so how the aerosol population will change, okay, due to this condensation or evaporation. Because the idea is so just to try to follow the drawing. Right. So let's say this is your population. Remember for different size. So let's say if we consider a condensation. So therefore, if you want to describe the change, right, the growth rates, the condensation. So you can imagine, at least intuitively, we know because this is the condensation, right, your aerosol will grow. So therefore, they will move to the right, right? The size will increase. So therefore, for a given size bin, so you can argue, right? So some will grow into this size bin. And then, of course, for this size bin, at the same time, they will grow. Right, they will go outside of this size bin, right? Are you okay with this? So that means if you look at a certain volume, right? So let's say if you focus on a certain size or certain volume, okay, aerosol with certain volume or size. So let's say I'm interested in looking at certain volume or size here. So you can argue, right? So some will grow in to this bin, right? So they will grow and become this size that we're interested. And then some will grow out, they become bigger, right? So they will outside this size range, right? So that means that you can argue. So there will be some we call the growth, we call growth in. And then you have some we call the growth out, right? So that would be kind of the idea, okay? So therefore, if you, for a given size bin, right, or a certain volume, so if you want to look at the time or the kind of the concentration, we can just do the mass balance, right? So you have something go in and then something go out, okay? So you can also looking at some of the kind of call the accumulation, right? Kind of the number concentration change with time. And just present in other ways called the influx minus the outflux, right? So you can use this kind of concept, right? In this case, just say this is kind of the grow in, right? Some smaller particle will grow and then become the size that we're interested. And then the size of this particle will grow and become bigger, right? So they will leave this size here. Okay. So therefore, you're trying to looking at this a given size. So how the number concentration, right, change with time, right? So you are looking at this here. Okay, so now you have this growth in and growth out. Okay, and then you affect the size, or you say the volume of your particle. Right? So that means your particle will grow in the size you want, but it also will grow bigger, right? So this is just the size you get interested. So this kind of a growth or condensational rate, so we have shown you before. So you can just use the notation. You can say this is a volume. So I just try to using the notation in the textbook. So basically, this IV is a kind of the growth rate, right? Just like that we mentioned, the condensational rate. Okay. Right, to change the kind of looking at the change in the volume. Now I just use the notation. The textbook is change the volume of a particle at a different volume, right? So this is kind of the change of the volume as a function of time. So this is just like the condensation rate, but we don't use the diameter, we use the volume. So V means the volume of your particle. Okay. And then just you can see, if you look at this term, just the diameter, right? You can also argue, right? This diameter, because this is the volume. Take the 1/3. This is just give you the diameter, right? So, and then this is the molar mass of your species. This is the diffusivity, right? Again, the diffusivity of your species in the gas, the corruption factor, and also the vapor pressure. So basically the same equation, but we just present in the way that you using the textbook. Okay. But the only things that now we are interested is to look at, okay, so when you have this condensation happen, right? Okay, so your size will change. And also for different size bin, okay, your number concentration will change, right? So that will be depends on your growth in and growth out, right? And then a different size bin, right? Different size. So the number concentration can change, right, due to this condensation process. Okay. Are you okay with this? So basically, you are looking at, say, for a given volume, particle volume, or different size, okay? So the number, right, within this size bin or volume bin will depends on the growth in rate or the growth out rate, right? So this is just a like kind of looking at the accumulation here, or the mass change, or the number concentration change. So therefore, if you want to look at, so how, say, the number, right, concentration of a given volume, at a given time, so how this equation means, so you're looking at, say, for a certain volume, a particle volume, right, the number concentration of the particle at a certain volume at a given time. So how they will change with time. So you're just looking at, this is we call the condensational rate, right? Condensational growth rate times for these given particle volume, right, at a given time. And then you're looking at so how you would change over time or over the volume. Then that will give you so how this number, right, at a different particle volume or size, right, size bin will change with time here. So these are some of the notation we use in the textbook. Okay. But before we continue, are you okay with using this with kind of the growth in and growth out? Okay. And then you're looking at the accumulation. So basically this accumulation, right? You're looking at the difference, right? Between the influx and the outflux. It tells you so how the concentration or how the number of particle, right, at this different size change, okay, over time. So you can describe by this equation here. So are you okay with this? Because maybe some confusion, but you can argue, you can looking at this, right? So you are looking at this is the number of particle, right? At the given volume that you are interested, right? And then you have some growth in and growth out. So for the growth in, you can argue, so this is just your IV, the growth rate, some smaller size, right? And then you're looking at the number concentration. So this is some smaller particle, they grow, and then you become the particle size that we are interested. And then you can also argue, right? So therefore, you are just looking at the difference between these two, okay? And then you just can come up with this equation if you're taking the limit of your volume and also the time tends to 0. So any questions so far? But if you don't worry about this, so in that case, I just try to use the notation of the steps following the textbooks, okay? But of course, most of the time, so we don't want to deal with the volume. So we can also using the diameter, right? So because most of the time, so the particle size, so we want to express in terms of the particle diameter, right? So therefore, you can also express this in terms of diameter. So basically, this is just the equation we showed you before. Actually, this is most of the equation that we just applied, right, for the condensational rate or condensational growth rate. So therefore, instead of using the particle volume, so you can using the diameter. So therefore, this term you just replace with some variable that we are feel more comfortable. So therefore, you can argue is to look at the n. So I just try to rewrite this equation in terms of using the particle volume, okay, using the notation in the textbook. I just change to the particle diameter, okay, in this term. And then this ID, this means just the condensational growth rate. So this is something that been discussed, right? So this is just the equation. And just for the classroom discussion, okay. So let's say we assume you're looking at some large particle, and then in that case, I just assume you're in a continuous regime. So I can just set this equal to 1. Okay. So if I can set this equal to 1, okay. So now you can see that so most of the parameters, so this equal to 1, right? So this will be equal to 1. And then if you look at all this, most of the parameters are the constant. The only thing is that this is the dP, right? This is when your condensational rate, right? The growth rate is just a function of dP, and then you have all kind of a constant A, right? So therefore, you can just rearrange this equation. I want to show you quickly. So we have the same discussion before. And because if you look inside this kind of a parameter here, so this is the diffusion coefficient, right, of your species I in the gas. This is the molar mass of your species I. This is the density of your particle, and then this is the vapor pressure, right? So most of the time these are the constant, right? So this is what we just set equal to A, right? If you remember. So therefore, your condensational rate, I just rewrite here. You can just argue just equal to A over dP, right? So this is just the I over A over equal to dP here. So A is just some kind of a constant, right? And then your condensational rate, growth rate is just a function of the particle size, right? And also you can see from this equation is your condensation growth rate, right, will be faster for smaller molecules. Right? So I think we also have discussed this before, right? For smaller molecules, so because of the surface volume ratio, so you have a larger condensational growth rate when you compare to some larger molecules. Okay, so now you can kind of idea about this condensational rate. I think because of the times, I want to take a second break here. Okay, so after the break, so we're going to using this equation, and then to help you to describe so how these kind of the change, okay, the size change, okay, over time due to this condensation growth rate. This is ID here. Okay, of course, it's a function of particle size. Okay, so let's because of the time, let's take another break. So one thing is, so I think you also get the message, right, from the program is we're going to do the OCTE for this class. So let's maybe, can I take maybe about a 30 minutes break? So we come back at 2 p.m. I hope that let's say during the break, can you spend some time to do the OCTE? So this is because the program encourage the course instructor to remind the student to do the OTE during the class, okay? Okay, so, and then that's why I want to say, let's take maybe 30 minutes break here. And I hope that you can take some time to finish the OCTE for the course lecture and also the TA. And also because of the progress, I just want to let you know that I'm going to also, because next week, so we don't have the class due to the holiday. So I'm going to have a makeup class on the April, okay? I think it's the 25th, okay, 25th. So we have a makeup class. So because I want to finish the coagulation with you also. I think today we can finish the condensation. And then I hope that in the last lecture for the makeup class, so we're going to finish about the coagulation. There may not be a 2.5 hour classes, but I want to finish the condensation, so coagulation with you. So we are going to have a makeup class also. We'll send you the details later, okay? But during the break, I hope that you take some time to do the CTE, and then I will come back at 2 p.m., okay? Okay, thank you. So maybe we just resume the class. So that's a question from the student. So there will be one more assignment for this class. I think TA Silam, are you here? So I think we will have one more assignment to answer your question. So that would be one more assignment. So in total 5. Is that okay? So because that's a question from the student, yeah. So that would be one more assignment. Okay. Good. Okay. So now we're going to finish for today's about the condensation. Okay. So now you can see this is kind of the growth rate. Okay. Or this equation is kind of the equation of condensation. Okay. So basically telling us, okay, so how, say, for a certain size bin, right? Or a certain particle size bin, so how the number concentration will change with time. Okay, of course, this will go to the growth rate, right? So you have a growth in and growth out. So therefore, we kind of want to solve this. These we call the condensation equation, right? So we try to solve this equation. So therefore, we try to look for a kind of a solution, right, for this condensation equation. Because like I mentioned, right, so on your left-hand side, this equation tells you, say, for a different size bin, right, so how the number concentration of a particle of a given size change with time, right, so due to this condensation or growth rate here. So if you look at this, so you can see this is actually, say, maybe I try to rewrite this equation again. So I just put this term to also to the left-hand side. So remember, so for this ID is a kind of the particle growth rate. So we just show you that that would be just equal to A. A is a kind of a constant, right? We group all the constant together. So for the whole term and then just divided by dp, right? So therefore the ID here, right? So these terms, so I just replace by this A over dp here. So you come up with this term here. Okay. I just rewrite this equation. And then you can see that this is just a PDE, partial differential equation. And then you can just somehow to solve this, of course, the first thing you need to expand this term, right? So expand this term. So I assume you have the idea, some idea about the mathematics. Is that you can see you have two terms here, right? So first, to expand these terms is that you can hold this A over dp, say, does not change, and then you take the derivative, right, of this aerosol size distribution function, right, with dp, and then you hold this dp, right? This is aerosol size distribution function, right? Does not change, and then you take the derivative, right, of your dp here. Okay, so you kind of expand these terms and then take the derivative. Okay, so by doing this, so I just rewrite the equation here. So I just expand this term and take the derivative. So first, this I just take the A over dP outside and then take the derivative, right, of your aerosol size distribution with respect to the dP. And then I can also take this a constant, and then I take the derivative of A over dP, right, by this dP here, then will be minus, right, A over dP squared. So I just minus and I put on the right hand side become positive here. So basically, this is a PDE function. And then you can kind of solve some this kind of PDE using some boundary condition. So first, your aerosol distribution, right, at a given size at time equal to 0. So that would be just your initial. This N naught dP is just your initial aerosol distribution, right? So before any condensation occur. And also, of course, when you have your aerosol size is 0, so at any given time t, right? So it's just equal to 0 here. And then if you're using this boundary condition, because if the particle size is equal to 0, so because always the growth, you can just assume it's always equal to 0 here. If you're using this boundary condition and then you solve this PDE, so you will find the equation. Okay, so what I'm showing here is this is your aerosols. Okay, number of your aerosols at given size and a given time will be equal to your particle size that you're interested dP, and then dP squared minus this 2 times AT. Remember, A is this term. This is the growth rate. So we put all the constant together, become 8 times the T, right? Of course, this depends on the T. So you have this dP squared minus 2A times T, right? Take the square root. N naught, remember, this is your initial aerosol size distribution, okay, function. But you just at a given size, so use your initial aerosol size distribution function. But you input the parameters, it's dP squared minus 2AT, take the square root. Okay, so this is how you can calculate, okay, for a given size, particle size at a given time. So what's the number concentration? So you can using this equation here. And one thing is, if you remember, so if we assume your initial, this is an N naught, this is your initial aerosol size distribution, right? So if you assume at the beginning, okay, your aerosol is a log normal distribution, So you can just substitute this term into your log normal distribution, right? So now the dP will become this term, and then you can substitute to your log normal distribution. Then by substituting into this, then you can come up with the equation. So there's nothing fancy here. Basically, you just if you remember, you have this log normal distribution function. And then now you set your dp equal to dp squared minus 2a times t minus 2a times t, and then take the square root, you substitute into your log normal distribution function. And then if you rearrange these equations, now you give you, so how your aerosol population change with time, okay, for different size. So how your aerosol population change with time, okay, or given time. So you have a kind of all these expression here, okay. Given your initial aerosol size distribution is a log, okay, so you can just substitute this and then rearrange this equation. So by solving this, but one thing is the more important. So what we can learn, say if you have a condensation, so how you affect your aerosol size, right, or your aerosol population distribution or your size distribution. Of course, you can using this equation, so you can double check with the textbook. So I assume every term that I'm presenting is correct. Then you can substitute the data, right? If you know your condensational growth rate, your A, and then this is your time, and then if you know your aerosol number concentration, okay, and also their variance, right, or the median diameter, and also their geometric standard deviation. So you can predict this. But most of the important thing is to get the idea. I think it's the most important is, of course, you have some idea about the mathematical calculations, okay. The more important is so how the population will evolve, right? So I think the most idea is if you say if you have some population, right? So initially, okay, you have a kind of a log long, right? The distribution here. So say time equal to 0. Okay. So what will happen, right, to these aerosol population if you have this kind of a condensation, right? So of course we know when you have a condensation, your size will increase, right? So therefore you should shift to your right hand side, okay? But one thing is that if you remember, the most important concept is to understand so how your size change is to go back to this term, right? So this is your condensation, right? Growth rate at a given size, and then will be equal to A over dP, right? So that means your smaller particle, if you look at this, if your dP is smaller, so they will grow faster, right? If you look at this equation. So that means that you can see here, initially you have a long distribution, but because the smaller particle will go faster, right? Will grow faster. So what will happen is, so now you will see, right? So I would just maybe just say at a certain time. So just a qualitative draw. But the idea is that you can see for the smaller particle, this part, right, for the smaller particle, so they will have a faster growth rate than your larger particle, right? So therefore, you can see eventually, so they will just tilt up here. So you will not, eventually, you will not see a kind of a normal distribution because of your smaller particle, right? In this case, the smaller particle will kind of go faster, right? So therefore, you will not see tilted here. So eventually, if you initially you start with a normal distribution, okay. So but when you have this kind of a condensation, you will not eventually you will not see a lot long, right, distribution. Does it make sense? Okay, good. So one last thing I want to discuss is in the lecture notes. I think the lecture notes give you a very nice ideas about a review about what we have been covered in the lecture notes. But one of the condensation and evaporation process. So what is important for study aerosol science? Okay. So I just want to give you one example. Is if you remember, right? So one of the important things for aerosol formation is the vapor pressure, the volatility, right? So most of the time, so to how to get this vapor pressure in aerosol phase, because you know the vapor pressure in the bulk phase and aerosol phase can be important, can be different. One thing is because of the Kelvin effect, right? If now you remember, this is a Kelvin effect, the curvature effect, right? smaller particle, right? So you have this curvature effect, you can enhance the vapor pressure, right? So therefore, if you really want to measure the vapor pressure in some submicron size particles, so you really want to look at is how the aerosol population or the vapor pressure at submicron size particle. So by doing this, so what people try to obtain this kind of a vapor pressure, they are not looking at the condensation, but they try to look at the evaporation. So that means that initially, if you say you have an aerosol population like this at the beginning, and then if you have the evaporation, because you can always expose the aerosol to some clean air, or you can apply some heating, then the aerosol will be evaporated. So let me see here. So you have this kind of like evaporation. Now we are not talking about condensation, but we are talking about evaporation, right? So if an evaporation, now your size will change. So assume this is more or less a monodisperse, not polydisperse. So then you have this kind of an evaporation. So what you can see, the example in the text, the lecture note is by measure the size change, okay? And then by solving this kind of the condensation equation, now you're solving the evaporation equation. You can also solve the vapor pressure. Now the thing is that you solve for is this term in your equation, okay? And then you can using this term and then convert back to kind of the reported volatility, or we say the vapor pressure, okay? So this is how people using the equation of condensation or equation of evaporation. One of the application is to determine the vapor pressure of a species by looking at the evaporation, looking at the size change, because this size change will be due to the vapor pressure difference, right? And then you can say that this is equal to 0, okay? So that you can determine the vapor pressure. So this is how most of the time people how to use this kind of condensation equation, or you can in this case call the evaporation equation to determine the vapor pressure. So this is the example I give you in the lecture notes. So this is a very important parameter to study the aerosol formation or many aerosol atmospheric processes. So this is one of the applications. Okay. So because of the time, I think I'm going to stop here for today. So, but before we leave so do you have any questions from the class? So there will be one more homework assignment, and then we're going to send you the guidelines for the details of the guidelines for your term project, literature review, and also presentation. Okay, and then we're going to have a makeup class on April 25th. So we're going to send you the details later. We're going to talk about the cooperation. But at last, so I think formally that will be the last lecture for this course. Okay, because the next one will be the makeup class. So I hope that you have learned something about the aerosol physics and chemistry, and then I hope that you also enjoy the material so we have been covered so far. Okay, and if not, then I think that will be the end for today's lecture. So likely we'll see you on next week. Okay, so thank you. Bye bye.